Thank you, Hannah. It's really awesome to be here where Faraday lectured. I'm paralyzed. But the show must go on. So I will be talking, as advertised, about a beautiful question, which leads us to insights about finding nature's deep design. This is the question: does the world embody beautiful ideas? It may seem like a strange question because ideas are one thing and embodiments are another. But there's a realization of embodied ideas that is very important to us. And another way of phrasing the question is the world a work of art? Because if you think about it, what art is embodying ideas, taking concepts, taking visions, and turning them into tangible realities. So is it useful to think about the world as a work of art? Can we do that in a way that's informative? And if it is it a good work of art? So I'll try to be addressing that question in the next hour. Let me begin with a crossroads of art and science that developed in the Renaissance, that is perspective. This will be a very fruitful way of introducing a concept that can otherwise seem very abstract, but turns out to be central, both in art and in science, the concept of symmetry. So, if you look from high up in an airplane, down at railroad tracks, they go for a long, long way and seem to be parallel to each other and never meet. But there are other ways of looking from different places, and if you look from different places, the appearance of railroad tracks can look qualitatively different. Here, for instance, we see that railroad tracks actually do meet. They meet at the horizon. And families of parallel lines all converge at a so-called point at infinity, or vanishing point. This leads to a question, which is, how do you do justice to the possibility of the same thing looking different? Can you portray that accurately? Or, in quasi-mathematical terms, what transformations can one make on an image while still having that image represent the same object seen from different places? That question is the question that the artists of the Renaissance really first addressed rigorously and led to the subject known as perspective in art and as projective geometry in mathematics. It's a truly wonderful subject, and I'll show you a lovely example of it in a moment. But first I want to relate it to symmetry. The implication of the fact that you can look at the same object and have different images of it is that you can change the image without changing what it represents. And conversely, if you have an object, you can look at it from different perspectives. You can look at it from different orientations, or far away from or near. If you look at it that way, you'll see different images. But the totality of images doesn't change. So you can rotate the object or move it far away or move it in all kinds of ways. That will change the way it looks, but it won't change the totality of representations that are valid. So this concept of change without change is the essence of symmetry, that you can perform transformations that could have changed something, but in fact don't. And it's that symmetry in common language is a kind of vague word. It's used as a synonym for some kind of balance. But in science, the precise version that's become very fruitful is this concept that you can change things without them changing. People find symmetry beautiful both intellectually and artistically. One of the joys of going back to these ideas was, for me, learning the art of perspective. And here is a joyful example of it. So the problem is, how do you represent a tiled floor that's tiled with squares accurately? What kind of operation on your canvas do you need to do that? And here it is. We talked about points at infinity. So we start with a square, and we start with a horizon, which is going to be where the points at infinity are. And we have the two sides of the square that we start with, that we're going to try to reproduce to tile the whole floor, meeting in this point at infinity here for those two sides, and that point at infinity over there on those two sides. How do we proceed to fill in the rest of it? Well, look at this red line. That red line is a diagonal of the square. We don't yet know where the other squares should be drawn, but we know that their diagonals should be parallel to the red line and therefore should meet in the same point at infinity. So we can draw the diagonals to the neighboring squares as these orange lines. Then we know one of the vertices of each of the neighboring squares, where the orange lines meet the blue lines. And we know that, therefore, two of the points that are on the square are these two that make a side. That should be parallel to this side of the original square, and therefore should meet the same point at infinity. So now we can draw in this side of the square in a way that's geometrically accurate and tells us how it will actually look. And then we can keep going. Okay? I won't keep going with this construction, although I highly recommend that you take it home and do it. It's really fun. And then if you erase the working lines, you get this beautiful accurate representation of what a tiled floor made of squares would look like from a different perspective. The artists of the Renaissance, Brunelleschi and his followers, who discovered this, were overwhelmed with joy. And you can see it, for instance, in this picture by Perugino, slightly afterwards. There's our tiled floor. And look how happy these people are to be able to play on an accurate geometry. Now I want to take it a step further, which takes us actually, as you'll see, to the heart of modern physics, our modern deepest understanding of the world. This is a generalization of perspective that's called anamorphia. Well, that's a word I made up, but it's called, the kind of art that's involved is called anamorphic art. And here we expand the concept of what changes we're allowed to make without changing the underlying object. So we expand the symmetry by having more possible changes that don't represent an actual change in the object. So here's a lovely example of anamorphic art. This column, which is reflected from here, would not look like this from any perspective, but reflected in a curved mirror, this is what it looks like. So we can make more transformations if we allow ourselves not only to look at from different places, but to allow distorting media to come into it. This same idea turns out to be at the root of our modern theories of the fundamental interactions. In particular, the first example of this was Einstein's general theory of relativity, which you can construct in this way, following out the words I'm about to say in equations leads you to the general theory of relativity. So to enable such generalized perspectives that allow all kinds of distortions in the appearance of things, in both cases, that is, in the case of space and time, where we want to allow objects to look vastly different, to have the anamorphic symmetry, and in both the scientific version and the artistic version. In art, the media that are used in order to enable these very different appearances to represent the same underlying reality are curved mirrors or lenses, as you saw. In general relativity, the corresponding medium, a fluid that fills space-time through which you see distorted images, is called the metric fluid. It includes distortions of space and time, kind of different coordinate systems, different ways of bending the image that still represent the same object. John Wheeler, who was a great wordsmith, poet of physics, responsible for words like black hole and concepts like mass without mass, summarized general relativity in 2 lines, which is space-time tells matter how to move, and I'll tell you what the instruction is momentarily, and matter tells space-time how to curve. So how does space-time tell matter how to move? It says move as straight as you can. But if space-time is curved, as straight as you can be a curved path. You do as straight as you can for short distances, but it curves over long distances. And matter tells space-time how to curve. This is the hard part of the theory. Where do you get equations that tell space-time what to do from the distribution of matter? And the way you determine the equations is by demanding that they have enormous amounts of symmetry, that they support, that this metric fluid supports a wide class of changes in the appearance of things without changing the underlying laws. This may seem rather abstract at this point. It'll become more concrete as we proceed. So our theory construction involves choosing the objects that we want to transform, the materials of the world, the sorts of transformations we want to allow, so the things that we want to allow to be transformations of the physical laws or of the appearance of things that don't represent changes in the laws of physics, and the material that enables those things to be reconciled, that there's different appearances and yet the same consequences. This art of theory construction therefore resembles step by step, the art of artistic creation, in anamorphic art particularly. That is, how did the artist arrive at that image of a column, that interesting distorted image of a column? Well, he had to specify what the substance is that he wanted to operate on, how you want it to look at the end, the kind of distortions you want to allow, and then what are the enabling materials that allow those distortions to be representations of the original image. It's an exact parallel to how we construct the theory of general relativity and, as you'll see, theories of the other basic forces. For later use, I want to refine Wheeler's poetry a little bit, because besides gravity telling things how to move, there are other forces that tell things how to move. And besides gravity telling things how to distort, besides the idea that matter makes a unique kind of distortion and has no intrinsic properties other than being matter, to tell space-time how to curve is a little naive. We have to be more specific. What is it about matter that space-time cares about? And the more refined version is the metric fluid tells energy momentum how to flow. And energy momentum tells the metric fluid how to flow. So the part of matter that's controlled by the theory of relativity, the general theory of relativity, is the concentrations of energy and momentum and their flows. And that's also what bends space and time. Now, that was a conceptual discussion of symmetry and kind of poetry about how it works in physics. Now I'd like to get a little more specific about it and root it in concrete phenomena. So a wonderful example of the symmetry of physical law is the theory of relativity in its original form due to Galileo. Galileo recommended this experiment to his readers. He said, with a ship standing still, look around, and you can, if you have little animals that you brought along, they'll fly with the equal speed in all directions, and the fish that you've conveniently brought along will swim indifferently in all directions. If you drop something, it'll fall straight down. And if you have brought along a friend and a ball to play with, you can throw it in either direction, and it's equally easy. That's reasonable enough. But Galileo's thought experiment of genius, was to say, let the ship be moving along in the ocean, and you're in this closed cabin. As long as it's moving smoothly, the same results will still happen. So you can change the physical situation by having everything move with a constant velocity, and yet the laws of physics won't change. That's the symmetry of relativity. You can't tell whether the ship is moving or not, even though arbitrary behaviors would change if you transform the world by transform the cabin by moving it, and motions other than constant velocity will tend to change things. You can have change without change moving at constant velocity. In his refinement of Galilean relativity, Einstein combined this Galilean symmetry with a powerful idea that the speed of light would not change as you move at a constant velocity. Velocities of most things would appear to change if you move along. If you're sitting on the outside of this cabin and watching how things move, they seem to move faster in one direction than another, but not if they're light rays. And this has one consequence that I find beautiful among all, most beautiful among all of them, which is that the different colors of light, which seem and were demonstrated by Newton to be the different colors of pure spectral light, to be things which don't change when you subject them to all kinds of indignities, reflecting them off mirrors or lenses or putting them through materials. A spectrally pure red beam will always stay spectrally pure red. A spectrally pure white, blue beam will always stay spectrally pure blue. That was a great discovery of Newton that revolutionized the theory of color. But there is a transformation, so it would seem that all the different colors of light are different substances that can change one into the other. But there is a transformation that does, and because its motion at a constant velocity shows that the different colors are related by symmetry transformations that don't change the laws of physics according to special relativity. That is, that if you move at a constant velocity past a light beam, what happens is that the light beam still moves at the same velocity, but its color changes. And so all the different colors can be related to each other by motion. And if you understand one of them, and there are transformations that change one into the other without changing the laws of physics, it means if you understand one of them, you understand them all. So that's the symmetry of physical laws, both as a concept, an example, and an example of how powerful it can be in unifying and simplifying the description of different things. Let me now describe a more abstract version, the symmetry of equations. So, because when we go to more unfamiliar realms, into subatomic realms where experience runs out and experiments get more difficult, we have to work not with thought experiments in ships, we have to work with equations. So inspired by that example, physicists learned to focus on equations that can be transformed in many ways. Those are the ones that nature seems to like. So if you take an equation and make a transformation on it, generally it'll turn into a different equation that means something else. But special equations, when you make transformations on them, can turn into equations that still have the same content, even though they look different, just like objects can look different from different perspectives. So here's an example, a real simple example. The only equation I'll have in this talk. The equation is x equals y. And that's obviously a balanced symmetric equation, you would say, between x and y. And it is, that intuition is borne out by the precise definition. Namely, you can make the transformation, changing x into y and y into x. The equation x equals y then turns into the equation y equals x, which looks quite different, but means exactly the same thing. So x equals y is a symmetric equation, whereas a lopsided random equation like x equals y plus 2, if you make the transformation, turns into y equals x plus 2, which means something entirely different. So symmetric equations are very special equations. going from that baby example to the frontiers of knowledge, if we assume that our equations will allow a wide variety of transformations, we get led to very specific equations. And that idea, symmetry of equations, is the essence of our deepest understanding of nature, our core theories. In the subatomic realm, where experiments are difficult and you can't follow the Baconian or Faradayan model of doing a lot of experiments to figure out what's going on, what you have to do is apply guesswork and aesthetic principles to guess what the equations are, and then check their consequences to see if your guesses are right. As a practical matter, that's how you have to proceed. And the miracle is that it works. Now, to discuss the other forces that appear in our fundamental theories of nature, I have to introduce another class of ideas. Fortunately, they are familiar ideas. So we can, although the realm I'm talking about is very unfamiliar and uncommon, I mean, is not something we experience in everyday life, there's a very, very close, uncannily close metaphor for it in our experience, in one aspect of our experience of the world, that is our experience of color. So let me elaborate on that thought. To understand the other forces, besides gravity, we need to introduce a new idea which is the idea of property spaces. As I mentioned, this is an idea we meet in everyday, in our perception of color. This is a picture of one of the great heroes of physics, the man who made the visions of Faraday into equations, the Maxwell equations, which we to this day use as our description of electricity and magnetism. And if you notice this picture of Maxwell, he has a kind of funny thing in his lap. Looks like a toy. What is such a distinguished person? Well, first of all, what is such a distinguished person doing looking like a kid? And then secondly, what's he doing acting like a kid playing with a little toy? Well, Maxwell actually was a very playful person, and you can see a little grin on his face and a twinkle in his eye. Anyway, what this object is a color top. And using that toy, Maxwell elucidated our perception of color in a very profound way. This is the underlying idea. The toy has two annular rings, and the rings can be overlaid with different colored papers. And if you spin it, you can compare the effective color that you get by the combination of colors, colored papers that are appearing in the outer ring, with the combination you're getting from the inner ring. What Maxwell discovered in a very long series of intricate experiments, largely in collaboration with his wife, is that you can take any color on the outside, and if you allow yourself to use three colors on the inside, you can match the perception of it. This is the basis of modern color photography, modern computer displays that display color. You can generate an arbitrary perception of color by mixing three basic colors. So this iconic figure shows how by mixing a beam of red, green, and blue, you can get white, or if you mix them with different relative intensities, any other color. So when you see in your computer options that say millions of colors, what those millions of different colors are actually 3 colors with different relative intensities. So it's a 3-dimensional space, perceptive color, as Maxwell discovered. And we can represent that using a color cube. So in the color cube, we have the amount of blue, the amount of green, and the amount of red. And at every point within the cube, of course, you don't see the interior here, but you can imagine what it is. There is a different perceptive color, and all the possible perceptive colors are represented. So the space of perceptible colors is this color cube. This gives us an entry into a very attractive kind of idea that's inspired many people over the ages, mystics, spiritualists, and physicists. That is the concept of extra dimensions. You can draw beautiful fantasies of what extra dimensions might look like. What would it be like to experience them? If only we could, wouldn't that be wonderful? Well, we can, and we do. In fact, remember this picture with the little spheres on everywhere? Now we have a color cube as a representation of the possible colors. And consider what you're seeing when you look at a computer screen. At every pixel, you're seeing a perceptive color, so some choice of a point in the color cube. In other words, what you're seeing is this. Almost the same thing. Well, the same thing as that representation of extra dimensions. And you can express this formally. If you want to give instructions to your computer what it's supposed to do, what it's supposed to be showing you, what you have to do is to tell it at every time t and at every position, x and y in the screen, how much red, how much green, and how much blue to show, what intensity of those 3 colors, what point in the color cube you should represent. In this formulation, it's hard to see a difference between these 3 numbers and that 3 number, those 3 numbers. Really, it's a 6-dimensional space. And so the answer to the question, what do extra dimensions look like, is you're looking at them. So with that in mind, I can now tell you about the other forces besides gravity by introducing a concept called anachromia. This is another word I made up. It's anamorphia of color spaces. So, property spaces of so-called color charges are the essence of our core theories of the other forces, the electromagnetic weak and strong forces. In electromagnetism, you've undoubtedly heard of the concept of electric charge, and the theory of electromagnetism is the theory of how the photon fluid, or if you like, the electromagnetic fluid, responds to distributions of electric charge. Electric charge is, at every point in space, a number, the density of electric charge at that number, at every point in space and time. So if you think about it, that's a one-dimensional property space. The theories of our other forces are based on the same idea, that is, charges, but in those cases they're called color charges, and they are two-dimensional spaces in the case of the weak interaction, and a three-dimensional space in the case of the strong interaction. So the world as seen by photons is this kind of monochromatic world. That's just the density of electric charge. The weak analogs of photons, the so-called weakons, respond to two different colors. So for instance, in this representation, one is green, two is green and red. And the strong interaction responds to three colors, three properties, three different kinds of charge, which actually uncannily are called color, although originally they had absolutely nothing to do with perception of color. Those three color charges make a three-dimensional space, which is what the color gluons of the strong interactions, the analogs of photons in that case, sense. Equations, so we have these property spaces, these like colored cube-like spaces that tell us about the charges and the weak charges, 2 dimensions, and the 3 dimensions of possible strong charges. And just as we could imagine transformations of space-time, very wide classes of transformations of space-time, and asking for equations that had symmetry under those kinds of transformations led us to general relativity, we can ask about deforming the color spaces, and we'll be led to very special equations that tell us that could be symmetric under anachromic transformations of the color spaces. So I showed you anamorphic art before. This is, as far as I know, the world's first attempt at anachromic art. It's not very beautiful, but okay. It's an open invitation to artists to improve on this. So here is an image of a candy stall in Barcelona, and you see it's a very colorful image. If I make a transformation that changes red into blue and green into red, I get this thing, and red into green, I get this version. Okay, so there's a transformation of colors that leads from this image to this image, and that can be thought of as a different perspective in the three-dimensional color space. And we might look for laws that look the same if we change these color spaces and look at them in different perspectives. Then we can look for laws which allow wider ranges of transformations where you change the colors in different ways depending on where in space-time you're doing it. This is the analog of anamorphic art, where you change the shape of space and time in different ways at different places. And that, if you do it in a gentle way, you can see here, you can modulate the colors. And if you do it in a more violent way, you get this. According to the concept of anachromic art, these all represent the same thing, just seen from different anachromic perspectives. As in general relativity, we find that if we want to enable these kinds of distorted representations of the distributions of different charges to represent the same physical situation, to obey the same laws of physics just seen through distorting media, we have to introduce such distorting media, and those distorting media have to have very specific properties. If we follow out this program for electromagnetism, we get the Maxwell equations. Those are the equations that allow so-called gauge transformations or local transformations of electric charge. the electric property space. And the yoga of QED, we can formulate exactly in parallel to the yoga of general relativity that I showed you before. That is, the photon fluid tells electric charge how to flow, just as before the metric fluid told energy momentum how to flow. And electric charge tells the photon fluid how to flow, just as energy momentum told the metric fluid how to flow. For more dimensions, for property spaces that are larger, we get more complex fluids, and instead of the Maxwell equations, we get something called the Yang-Mills equations. These are like the electromagnetic fluid on steroids, and like the Maxwell equations on steroids. When you go from a one-dimensional property space, which you have in electromagnetism, to the two-dimensional property space, it turns out that the fluid you need to make to enable the transformations to be the local transformations of color to be symmetries of the equations. The fluid you need has three components. Instead of one photon, one electromagnetic field, you get three so-called weak ons, or weak W and Z boson, W plus, W minus, and Z bosons as physical objects. In the strong interactions, you're led to 8 photon-like objects, the color gluons. But it's the same procedure, really, at a deep level, as we use in general relativity and in electromagnetism to generate laws based on symmetry. So the yoga of QCD is that the gluon fluid tells the strong color charge how to flow, and the color charge tells the gluon fluid how to flow. And in all these cases, I could have put the stars and the double stars that I had for general relativity. What the gluon tells strong color charge to do is keep your color as constant as possible, to keep moving as straight as possible in color space. And what the color charge tells the gluon fluid to do is make symmetric equations. And that leads to our theories. I'll leave the yoga of the weak interactions to you. So in this way, we discover a common dualistic conception from which all the known interactions flow. People found such dualistic understanding beautiful long before anyone knew that it governs the fundamental laws of physics. In fact, in Chinese philosophy, we have yin and yang. Yin is the substance. Yang is what pushes it around. And so it's like yin are the electric charges, and yang is the electromagnetic field that pushes them around. Yin is energy and momentum, and yang is the metric fluid, which pushes it around. Yin is substance, yang is force. Each responds to and is shaped by the other, and each contains an aspect of the other. That last one is that in quantum theory, we learn that the force carriers also are particles. So the electromagnetic fluid gives rise to particles called photons. And as I've already alluded to, the gluon fluid gives rise to particles called gluons. So they have a yin-like concrete reality as well as a force aspect. Now, from all these considerations of art on the one hand and the laws of physics on the other, we can get a beautiful answer to our question. An empirical answer, I should emphasize. Right? It may sound like a question that can't be addressed empirically. Does the world embody beautiful equations? But we can gather evidence about what beauty is And we can gather evidence about what the world is to see if the world embodies beautiful ideas. So let's do that. Seeking to embody divine beauty, artistic creators anticipated the spirit of anamorphic art and of anamorphia and anachromic creativity long before anyone knew that it runs the world. Here it is. For example, take a look. You see the richness of shape, the changes of color that are characteristic of our deep understanding of nature were already things that people found beautiful long before they knew that that's how the world worked. So, does the world embody beautiful ideas? By experiment, yes. Which beautiful ideas? Well, exuberance of form, you get richness of structure from simple underlying rules. Remember those people playing on the grid in Perugino's work? That's the kind of exuberance that nature shows in using simple rules to make complex substances like you and me and the things that appear in chemistry from these simple underlying rules. Exuberance of color, and even the underlying concepts of symmetry and dualistic understanding, Taiji or yin and yang, are all things that people found beautiful and important in understanding how the world works before they knew that that's the way fundamental laws work in physics. So that's history. Now I'd like to show you how we want to build on this to guess new improved laws of physics, perhaps. As I mentioned, our way to make progress in fundamental understanding has been to guess the equations based on aesthetic considerations, specifically on the kind of generalized symmetry I've discussed with you. And now, let's see if we can make another big step. So, with this dualistic conception of forces on the one hand and substance on the other, we have not quite achieved a unified description of nature. There are two things. Two is more than one. Can we transcend that dualistic description to get a truly unified theory? In other words, can we make a transformation that changes the yin into the yang and the yang into the yin, but doesn't change the behavior of the physical world? That kind of symmetry, if it existed, would show us why there are two substances, two different things, and why either one implies the other. So, in that sense, there's only one thing. Just as there's only one light, because you can transform the different colors all into one another by transformations that don't change the fundamental behaviors. So, to accomplish that trick, we must extend Galilean symmetry, which was the symmetry of motion, allowing motion into a new kind of dimension, a so-called quantum dimension or superspace. When you make that kind of transformation, if you're a force particle, you change into a substance particle. If you're a substance particle, you change into a force particle. So it's quite a drastic transformation. Not for the faint of heart. it was kind of a harrowing experience to go. But it's an eye-opening experience. Because what you find that if you expand the equations we have, adding materials that allow this new kind of transformation between forces and substances, you have to expand the equations, add more stuff, and that stuff turns out to have a salutary effect on the way we understand forces in other ways. In our account of the forces of nature, I mentioned that there were 4 of them in our fundamental description: the strong, weak, and electric forces. Those have very different powers. The strong interaction really is stronger than the others. And gravity is much, much weaker as it acts between fundamental particles. But we might ask the question whether, if we look closer, if we look at short distances, strip away some of the complications of virtual particles and distortions produced by activity in empty space, whether the underlying forces at very short distances are actually equal. It turns out that if you include the distortions due to the new particles you introduce with supersymmetry, then it all works. Whereas if you don't, if you just use the paltry particles we have, it almost but not quite works. So this attempt to make the equations more beautiful has consequences that seem to be verified, but they're kind of indirect consequences. They are things about extrapolating the laws to short distances that are conceptual, not directly experimental. And the question is whether the new expansion of the laws and the new particles that you need to make supersymmetry, whether they really exist. Is it a revelation or an illusion that you get this unification? Well, at the Large Hadron Collider, which is now ramping up again at CERN near Geneva, you have this exact question being addressed. It's a fantastic engineering project. It's a tunnel 26 kilometers around, circular, where protons are accelerated to extraordinarily high energies. You use superconducting magnets to guide them. These magnets have to be at 2 degrees Kelvin, which is colder than anywhere else in the universe. This is the coldest. Even interstellar space has the microwave background radiation at 3 degrees or Kelvin. This cryogenics extending for 27 miles and cooling these magnets is not easy to maintain. You can see it's an exhausting task. But as a result of these explorations, we will find out in the near future whether those ideas that extend the successful guessing of symmetry and unification that's led us to our present understanding of nature, and that fulfills some aspects of the artistic aspirations that people have had for a very long time, whether those actually, again, give us new insights into the way things work. So, for all this discussed in depth and much more, I can't recommend too highly this wonderful book, and the cover alone is worth the price. You see, you get to look through open it up, look through the peephole, and see that the deep structure of reality is richer than the surface appearance, and that its deep structure is deeply artistic. So thank you very much.